Hi everyone. In the previous lecture, we discussed about a brief history of the genesis of cascode amplifiers. We saw how engineers at that time chanced upon the cascode amplifier structure starting from a simple a simple common cathode triode amplifier. Now in this lecture, I'll try and give an intuitive reasoning as to how one can derive a cascode amplifier structure starting from a common source amplifier. Now mind you, this may not have been the thought process of the engineers who had chanced upon the cascode amplifiers. This is something one can, with the knowledge of circuits that we have today, we can intuitively think that we can arrive at that structure. So for our discussions, we'll start with the common source, the conventional common source amplifier which is shown here. And for the purpose of our discussion, to better understand the usefulness of a cascode amplifier and to show the advantage of a cascode amplifier from a high frequency analysis point of view, I'm going to assume only one capacitance CGD. So here the assumption is this common source amplifier is driving a resistive load. So you can have resistive loads or capacitive loads. Here it's driving a resistive load, which means the capacitance is negligible, load capacitance is negligible. Now under these conditions, we will try to analyze and see what is the frequency response of this circuit. Now here, of course, there will also be a source resistance. I have not shown it yet. I will show that probably as we progress into the lecture in a few moments. Now this input voltage, it's trying to charge, this is the input voltage which is fed to this common source amplifier connected to a resistive load. The DC gain of the circuit is minus of Gm times RL. So you have this drain current GmVi flowing into a load resistance. So you will get minus of Gm RL as the DC gain. So eventually the steady state voltage here is minus of Gm RL times Vi, and this node voltage is Vi. So the total voltage this capacitance CGD is being charged to is CGD into 1 plus Gm RL times Vi. And all the charge has to come from the input voltage, because this current here is 0, so this charge has to the charge that is being delivered to CGD has to come from the input voltage. So therefore, if you recall, the input is trying to charge this node to Vi, but to do that, it has to supply a charge equivalent to this, CGD times Vi. So the input is going to think, for this voltage, I am delivering this amount of charge. So the capacitance that is seen at the input terminal is a large amplified version of CGD, which is CGD into 1 plus GMRL. So this is called Miller effect or Miller multiplication. The capacitance is going to get multiplied by the gain of the circuit, and it's going to appear as a huge capacitance at the input port. Now, the problem of Miller effect is that the problem this capacitance create, what problem does this create is that the input source has a finite source resistance, and when that source resistance sees this large multiplied cap, which is CGD into 1 plus GMRL, we are going to have a very low frequency pole because of this. The low frequency pole will occur at 1 by RS into CGD into 1 plus GMRL. This is 1 plus GMRL. So the larger the gain that we are designing this amplifier, the lower will be the low frequency pole. So the lower will be your bandwidth. So that was the problem in a conventional common source amplifier, that the bandwidth was dependent on the gain as well. The higher the gain we design this for, the lower will be the bandwidth. Now, can we solve this problem somehow? If we want to intuitively solve this problem, we have to identify what is the source of the problem. The source of the problem here is that this capacitance getting multiplied by a large value, and that's happening because on the one side you have Vi, on the other side it is getting charged to a really large negative voltage, which is proportional to Vi. It's getting charged to minus of GMRL times Vi. Now, what we need to do is that if we can somehow calm down this node, meaning if we can somehow reduce the voltage at this node without affecting the gain of this amplifier. So which means the load resistance RL needs to receive a current of GMVI It needs to receive that current of GMVI. But I don't want to have much variations at the drain terminal. So I am going to decouple the drain terminal, which is already carrying a current GMVI. I need to transfer the same current from here to here. But I need to ensure the voltage variation at this node is much smaller than the voltage variation here. So then to do this, I am going to use a circuit which can offer a very low input impedance. It's going to offer me an extremely small input impedance. So which means it's going to absorb all the current which is being fed to it. And it's going to deliver the same current at the output. And it's going to have such a high output resistance. The output resistance of this device will be so high that most of the current that it is going to output will flow into the load resistance. And that device is nothing but a current amplifier. A current amplifier by definition has an extremely low input impedance and a very high output impedance. So it can draw, if I feed an input current GMVI, it can transfer the same current to another node. But now these two nodes are isolated. This node and this node are properly isolated because I've inserted a block in between. And this, since we are delivering the same current, this happens to be a current buffer. Now if you see, the input impedance of a current buffer is exceedingly small. For example, we can assume the ideal input impedance is nearly 0. If the input impedance is 0, then the voltage swing, the variation at the output voltage at this node will be GMVI, the current at that node, times the input impedance there, which will be 0. So the change in voltage at this node is 0. Now you see at the output terminal, since the load resistance is receiving the same current GMVI, the output voltage will be same as it was in a conventional common source. In a conventional common source, the output voltage was minus of GMRL times VI. Even now, the output voltage is the same. Because you are receiving the same current times the resistance, you will get this voltage. So which means the voltage gain is still the same. But what we are doing here now is that this capacitance CGD, the drain, the other voltage of this node, of this capacitance, is no longer at an amplified version of the input voltage, but rather it is at ground, AC ground. So that's what I've shown here in this figure. So if you see this figure here, by introducing a current buffer, I've introduced a current buffer whose impedance is 0. I have ensured that the small signal voltage variation here is 0. So of course this is biased, so it will have some DC voltage, but the AC voltage, the small signal voltage will be 0 here. Because the input impedance is 0 and a finite current times a 0 input impedance will be 0 impedance at this node, it will create a 0 voltage. So therefore this will not see any variation at all. So this node will be calm or calmer than what it was before. So the total charge that the input has to deliver to this capacitance, let this node voltage be VI, you will have to now charge it to just VI itself. So you are delivering a charge of CGD into VI. So at the input, if you see at the input, since this node is at AC ground, the effective capacitance you are going to see here is just CGD itself. So now we have solved the problem of the reduction in bandwidth in a conventional common source amplifier by introducing a current buffer. By introducing a current buffer, I could solve this problem of capacitance multiplication. Now at the input port, you have a resistor RS. Now the capacitance is just CGD itself. It's no longer CGD multiplied by a large gain, it's just CGD itself. So therefore the pole will be now at 1 by RS into CGD. So previously the pole was at 1 by RS into CGD into 1 plus GM RL. Now if you see here, the pole has moved away, or rather the bandwidth has increased by a factor of 1 plus GM RL. It is increased by a huge factor. Now the next question is, it looks simple here to show that, okay, we assume that there is a block we have introduced which can offer a very low input impedance and deliver the same current at the output. So it's a current buffer. But now the problem is, in implementing this, we need to choose a circuit which is very simple which also doesn't suffer from the problem of Miller multiplication, and it should serve as a good current buffer. So the condition is low input impedance, high output impedance. And since we have already studied MOS amplifiers, we know readily a common gate amplifier satisfies all those properties. The input impedance, if I neglect R0, is negligible. It's just 1 by Gm for a common drain amplifier. Output impedance is very high. If you look into the drain terminal, it's at least R0. If you assume R0 is infinity, its output impedance is just infinity for this common gate amplifier. And luckily, there is no capacitance connecting the input and output terminals. So there is no Miller effect, possibilities for Miller effect in a common gate amplifier. So this current buffer, we are going to replace it with a common gate amplifier. But since the common gate amplifier, it's not an ideal current buffer, the input impedance is not 0 in this case, now it's going to be 1 by Gm. So the small signal AC voltage at this low frequency AC voltage at this point will be minus of GMVI is the AC current times the impedance, which is 1 by Gm, so it will be minus Vi. So now this node is now being charged to minus Vi. An ideal voltage current amplifier, it was 0, but now it's being charged, it's because you have a finite input impedance, it's being now charged to a finite voltage, which is just minus Vi. So this capacitance CGD now has to be charged to a voltage of 2 times Vi, which is much smaller than 1 plus GMRL in a conventional common source. So therefore, the equivalent capacitance seen at the input, this node is being charged to Vi, but it is delivering a charge of CGD into 2 Vi. So at the input, it's going to look like a capacitance of value 2 times CGD. So now remember, from a common source amplifier, it was CGD into 1 plus GMRL. And we said, as we increase the voltage gain, the capacitance was getting multiplied by larger and larger values. But now if you see here, it is independent. Even if you change the load resistance, it doesn't matter. The input capacitance will always be 2 times CGD. So therefore, we have decoupled the gain bandwidth dependence. The bandwidth was dependent on gain. The larger the gain, because of Miller multiplication, we were seeing smaller and smaller bandwidth. We have decoupled that problem and we have now extended the bandwidth significantly. So for comparison purposes, I have shown 3 plots here. Shown in pink here is the response of a common source amplifier with a resistive load. So here you can see the pole is at 1 by Rs into CGD into 1 plus GMRL. Now mind you, the gain in all the 3 examples we took, a simple common source plus a current buffer, this one, a common source plus a common gate. In all the 3 configurations, the voltage gain is the same. We are delivering the same current to the load resistance. So the voltage gain is minus of GMRL, that is fixed. Magnitude is plus GMRL, that is fixed. The difference, however, is in the input capacitance. We have assumed only CGD in the analysis, and we showed that in case of a common source amplifier, because CGD gets multiplied by a large factor which is proportional to the DC gain of the circuit, if you design it for a high gain, the capacitance gets multiplied by a much higher value, and therefore the bandwidth reduces. So we said, shown in pink here, the bandwidth of a common source is very less. Then we said we will introduce a current buffer and we can extend the bandwidth all the way to 1 by Rs into CGD. We said the input equivalent capacitance is just 1 by CGD, we could extend it to that high value. Then we said in practice, since we are going to realize it using a practical circuit, in this case a common gate amplifier, we can still, the input reflected capacitance will just be 2 CGD. So the bandwidth increases compared to a common source, but not as high as an ideal common buffer, a current buffer. So in this case, it's going to be 1 by 2 times Rs into CGD. Now the important thing to keep in mind here is that even if I increase RL to increase voltage gain, this bandwidth keeps reducing here. Gain increases, bandwidth reduces. But in this case, in case of a Cascode amplifier, the bandwidth is immune to gain. It is always 1 by 2 times Rs into CGD. That's the major advantage in a Cascode amplifier. It solves this problem of bandwidth reduction in a common source amplifier by introducing a common gate amplifier in between this common source, the amplifying device and the load resistance. So this combination of common gate plus common source plus common gate configuration is what we call cascode configuration. Now remember, the name is derived from vacuum tube amplifiers, but since behavior wise it's very similar to that, we call this also as a cascode amplifier. So now for comparison of bandwidth, in case of a MOS cascode amplifier, CMOS cascode amplifier, the bandwidth of a cascode amplifier here is 1 by 2 RS into CGD. That's your 3 dB bandwidth. It's a single pole system, so I'm just treating it as 1 by 2 as 1 by 2 RS into CGD as its bandwidth. The bandwidth of a common source amplifier is 1 by RS into CGD into 1 plus GMRL, which is much smaller than this. So the ratio of the two, the bandwidth of cascode is going to be larger. It's larger by a factor of 1 plus GMRL by 2 times the bandwidth of cascode, a bandwidth of common source. So this is the bandwidth advantage we get in cascode, and this advantage we get mainly if you are driving resistive loads. I'm making that point very clear. We are driving resistive loads and not capacitive load. That's when you get this benefit, and CGD is the major dominating capacitance. Now to quickly extend it the same way to the BJT, I can explain it similarly for a bipolar junction transistor as well. In a BJT we have C pi is the gate, like a gate to source capacitance, it's your diffusion capacitance. C mu here is the base collector reverse biased PN junction capacitance. Now the C mu capacitance will be Miller multiplied by a factor of 1 plus GMRL. So this is a common emitter configuration. So the total input capacitance seen here will be C pi plus C mu into 1 plus GMRL. So if I increase load resistance or increase transconductance GM, this term is going to increase significantly. So the higher the gain, the lower the bandwidth. That's what we are seeing from this expression. So now we are going to introduce a common base configuration in between the common emitter and the load, and this is what we call a BJT cascode amplifier. It's going to give us the same benefits. The input capacitance now, because of C mu, will just be 2 times C mu. Okay. However, I mean, it was very similar in case of a MOS cascode amplifier as well. Roughly, we can say it is 2 C mu. Here again, I'm stressing it. All these advantages are because of the load resistance. The load being a resistive load, we get all these benefits. If it was a current source load, it's a different scenario. We'll analyze it towards the end of the lecture. So we are going to get, especially when amplifiers are driving resistive loads, we get a huge bandwidth advantage. That's one of the main selling points of cascode amplifier. It comes with other advantages as well. We will discuss as we go on with the lecture. So now I'm presenting all the 3 cascode amplifiers in vacuum tubes. This one is in vacuum tubes. The idea was developed in 1930s and it was popular for almost 3 to 4 decades. In 1960s, BJT transistors took over. So BJT was properly implemented in 1950s. 1951 was when a proper BJT was manufactured. And in 1960s, once MOS was invented, we had cascode structures in MOS amplifiers as well. So the devices kept changing, but the fundamental idea remained. The idea of cascoding a high gain amplifier followed by a current buffer, wherein it can give you a higher bandwidth if your source resistance is very high. So that's it about the introduction to cascode amplifiers. Now we will look at the benefits that cascode amplifiers offer. One major benefit of cascode amplifier is input-output isolation. Isolation is very important. You don't want changes at the output to sometimes a part of it to creep into the input and affect the input circuitry. So isolation is very important, and we will see cascode amplifiers provide very good isolation between input and output ports. And higher bandwidth for resistive loads. If the load is resistive, typically the load is resistive loads, then we get the bandwidth advantage, which we already discussed in the first half of the lecture. Third one is higher output resistance. Now this is the property which is exploited in current integrated circuit CMOS amplifiers to get high gain out of cascode amplifiers. If you recall, so far when we were discussing cascode amplifiers, gain was not the reason why we went for cascode. There, the main reason why we went for cascode was extended bandwidth. But we will later see in a few moments, gain is also one major reason why we resort to cascode amplifiers, in especially low frequency circuits, low frequency high gain amplifying circuits. Now before we go ahead with our analysis and I present the comparison of the advantages in detail, I'll first analyze cascode amplifier with a capacitive load. I'm ignoring all the other capacitors in the circuit. I'm going to consider only one capacitance at the output terminal, CL. You can assume that we are driving it with a current source load, ideal current source, RL is infinity. So here it's very clear RL is infinity. Now we will try to compare this with a conventional common source amplifier. Now we said when we analyzed cascode amplifier low frequency analysis, we said this cascode amplifier can be represented as a short circuit transconductance GM times output resistance and output resistance R out. And the short circuit transconductance GM is the GM of this device. So you measure it by short circuiting the output node, apply an input, so you have a current GM1 VI flowing here. The same current will flow through the output terminal as well. So since I'm assuming both these devices are identical, so you get the short circuit transconductance as GM. If these two devices were different, say this is 1, 2, this would have been GM1. But let's assume they both are same, so the short circuit transconductance is GM. And the output resistance of a cascode amplifier, this is something we have already discussed in much greater detail. For a cascode amplifiers, we said cascoding more and more devices gives you higher and higher output resistance. That's one of the reasons why we go for cascoding, to get high gain. So the output resistance is given by GM R0 square. So the RO of this device, R0 of this device, multiplied by GM R0 of this device. That's the output resistance. So here it is GM R0 into R0, so it is GM R0 square. So the DC gain is A0 is given by minus of GM R0 the whole square. This is the maximum attainable gain in a common source cascode configuration. Now shown here is the circuit representation as far as the capacitor load is concerned. So from this circuit I can directly derive the expression for the gain to be minus of GM R out, the DC gain, times divide into 1 by 1 plus S R out CL. This is the transfer function of this circuit. Now I have written the transfer function here. This is minus GM R naught the whole square by 1 plus S CL R out. Now the pole for the circuit is at 1 by CL R out. So it's given by 1 by CL into GM R naught square. The gain bandwidth product, the DC gain, is minus of GM R naught the whole square. I am taking the magnitude of A naught times omega p, which is the 3 dB bandwidth, you can directly very easily show it's GM upon CL. Now if you compare this with a common source amplifier, the DC gain is GM R0 minus GM R0. The DC gain for a cascode is minus GM R0 times GM R0. So it's GM R0 the whole square. So it's getting multiplied by GM R0. It is getting increased by a factor of GM R0. The pole, however, for a common source amplifier, the pole is at 1 by R0 CL. So this is the common source amplifier. We have already analyzed the circuit. The pole is at 1 by R0 CL. But for a cascode amplifier, the pole is at 1 by CL into R out, which is 1 by CL R0 times GM R0. So your output resistance is increasing by GM R0. Therefore, pole is decreasing by GM R0. So what we are seeing here is that the DC gain is increased. So if I write A0, mod of A0 cascode is mod of A0 CS times GM R0. The DC gain has increased by GM R0. But the pole, the 3 dB bandwidth, the omega p cascode has decreased by a factor of GM R0. So omega p CS upon GM R0. So the product gain into bandwidth product remains the same. So that's what I have shown in the frequency response graph here. If you see in this graph, so this is the gain for the frequency response for a cascode amplifier. This is one for a common source amplifier. The DC gain has increased by a factor of GM R0, but the pole has decreased by the same factor GM R0. So for a common source, even though the gain is reduced by a factor of GM R0, the bandwidth is much higher. So this analysis is for capacitive loads. RL is infinity. and I'm assuming there is a large capacitance at the output, then what we are noticing here, the advantage offered by a cascode amplifier is not in terms of bandwidth, but in terms of DC gain. DC gain is the benefit you get out of this. The gain bandwidth product remains the same. If you're driving a capacitive load, the gain bandwidth product of a common source and a cascode amplifier remains the same. But the advantage you get in cascode is the DC gain. The DC gain is much higher as compared to a common source. And this is a very important property, especially when we are building high gain amplifiers called operational amplifiers. We will see cascode amplifiers are used often to realize high gain. So here we can see after we cross the pole 1 by R0 CL, the transfer function for both the circuits. So if you see this circuit here, once we cross 1 by CL R0, I can ignore 1 here. So the transfer function becomes minus of GM by SCL. In the same way, I can ignore 1 here as well at high frequencies. This transfer function will also reduce to minus of GM by SCL. So that's what the transfer function here will be, GM by SCL. So the point where it touches the unity gain or 0 decibel line is when this becomes equal to 1, that's your frequency at that point will be GM upon CL. That will be your gain bandwidth product. So here the assumption is that the DC gain GM0 is much greater than 1. If we make that assumption, then we can easily show this frequency where the amplifier's gain becomes equal to unity. It's called the unity gain frequency, will be GM by CL, which will be exactly same as the gain bandwidth product. The gain bandwidth product. So that's the difference between capacitive load and resistive load. So to summarize, when we were driving a resistive load, we saw that the benefit, the gain, DC gain was same for common source and cascode. The benefit there came in terms of capacitance multiplication. The input pole, because of the source resistance, could be extended, could be pushed away to higher frequency in a cascode amplifier. That was the benefit there. Whereas in a capacitive load, when you are driving a capacitive load with no resistive component, which means RL is infinity, the benefit is in DC gain. You get much higher DC gain in a cascode amplifier. The bandwidth is reduced, DC gain is increased, but the gain bandwidth product remains the same. It offers the same gain bandwidth product as a common source amplifier. So we don't get the bandwidth advantage when you're driving capacitive loads. So that's something to keep in mind. But when we are driving resistive loads, bandwidth advantage definitely comes into play. The next thing, now I'm going to look at the advantages offered by the cascode amplifier. One, we discussed bandwidth advantage with resistive loads, which is fine. Second is gain advantage. We can get much higher gain from a cascode amplifier than a common source for capacitive loads. And that gain is attained by increased output resistance. Because of increased output resistance, we're able to get higher gain. So that's the benefit. That's the other benefit of cascode amplifiers is higher output resistance, which leads to higher DC gain. The third and the important gain advantage of a cascode amplifier is input-output isolation. Now let's look at a common source amplifier here. Because of this capacitance CGD, if I apply some noise at the output terminal, so I'm calling it delta Vx here, at very high frequencies, this capacitance is going to act like a short circuit. Then the amplifier is letting in all the changes at the output terminal to the input side. So we don't get proper isolation between input and output. So that's the problem of isolation here. In fact, we can rigorously analyze this and show that there is a high pass transfer function from the drain terminal to the gate terminal. So the high pass transfer function would look like this. At high frequencies, the gain will be 1 or 0 decibels. So which means most of the signal at the output can be coupled back at the input. So keep in mind, this is not feedback. Feedback is intentional. Sometimes we introduce feedback for getting some benefits out of the circuit. This is unintentional or parasitic feedback. We don't want it, but it happens, and it's detrimental to the circuit's operation. So that's so we want to avoid this. We want to be able to isolate input and output ports so that no output can leak into the input side. Cascode helps in that very well. So shown here is a cascode amplifier. If you see, there is no capacitance which is connecting these two terminals. So there is a resistance R0. If I ignore R0, And if there is some noise, say unwanted signal delta Vx at the output, this common buffer here acts like a shield between this and this terminal. So therefore, even though this node voltage is changing, if R0 is infinity, you will not see any change in this terminal here. So therefore, you get very good isolation between the input and the output. So that's other benefit a cascode amplifier offers. We don't want any output signal to be coupled back to the input. So that's what isolation is for. That's isolation. And cascode amplifiers give you very good isolation, and the isolation comes from the common gate structure. It's the common gate which provides you the isolation, because the reverse gain of a common gate is very less. We saw that approximately if you include R0, it will be very close to 1 by GM R0, 1 by 1 plus GM R0. So it's attenuating the signal significantly. So that's where the benefit for isolation in cascodes comes from. So this is what we have discussed about cascode amplifiers. We listed out its advantages. We looked at historically how cascode amplifiers were developed first. We saw the benefits cascode amplifiers offers for resistive loads. If you're driving a resistive load, then definitely bandwidth, especially if with a large source resistance, you get a huge bandwidth advantage. If you're driving a pure capacitive load, then you get a much higher DC gain compared to a common source. The comparison is always with the common source. And we also saw the 3 dB bandwidth is lower in cascode. You don't really get bandwidth advantage if you're driving capacitive loads. Okay, in that case the advantage is mainly in terms of the DC gain, and the gain bandwidth product remains same. It's very similar to a common source amplifier. The third advantage is isolation between input and output. These are the three major benefits of cascode amplifiers. So with this, I've completed the discussion of a cascode amplifier. I'll probably try to do a more rigorous analysis of a general cascode amplifier considering all the parasitic capacitors in the next lecture. Thank you.